Hello everyone. Sorry for the canceled class. So as I announced on the Blackboard, so I was held in extremely heavy traffic. That I think that it is because of bus drivers strike and actually the car accident in the route. So I was so unlucky today. So anyway, sorry about that, and then sorry about the late announcement because I tried to call the TAs, but TAs did not respond, and then also I was driving, so I was not able to type, and I was not able to make an announcement on the Blackboard. So okay. So anyway, sorry for the canceled class, and then sorry for your inconvenience. Okay, and then sorry for your some wasted time. Okay, so I will record the today's lecture. And then so what we learned in the previous class. So we learned how to build basic logic gate using transistors. So for the transistor, actually the behavior of a transistor is a little bit tricky to understand, but actually we need to analyze the real behavior of transistors in an analog manner. Okay, but actually we can understand. So we can understand simplified. We can simplify the behavior of transistors by using a digital discipline, right? So you can understand that a transistor is a controllable switch, right? As I mentioned in the class, you know, the the connection between drain and source is controlled by the gate voltage. So it's a gate signal level, okay? And then also, so we can build a basic logic gate using a transistors, but we need to use both NMOS transistors and PMOS transistors for building basic logic gate. So it is because of real behavior, real characteristics of the MOS transistors. Okay, so as you can see, NMOS pass good zero, so which means that if the some voltage is zero, then NMOS can transfer these values to the another node. Okay, then also PMOS pass good one. So that's why the PMOS is connected to the VDD, and then NMOS is connected to the ground. Okay, and then also I explained that the NOT gate. So by combining PMOS transistors and PMOS transistor and an NMOS transistor, then we can build a NOT gate. Okay, so actually so as I mentioned, we can understand the behavior of most transistors in a digital manner. Okay, like so if the gate is given, a gate signal is set, then the NMOS transistor or PMOS transistor can be connected or disconnected. So the output can be high voltage or output can be low voltage. So 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 using for this circuit, so as you can see for this circuit, we can implement an inverter circuit by using one PMOS transistor and one NMOS transistor. Okay. Also, I also explained about the NAND gate, and then also and then NOR gate. So NOR 3 gate. Okay. But so I also explained that actually in order to implement AND gate and OR gate, so okay, so actually we need to implement AND gate and OR gate by combining NAND plus NOT gate or NOR plus NOT gate. Okay, so actually we cannot directly implement AND gate or OR gate using this CMOS transistor circuit. So actually, we need to combine NAND plus NOT or NOR plus NOT for implementing AND or OR gate. Okay, so like this. And then also I explained about the transmission gate. So this is the switch. Actually, it's a true switch, but we need to combine the NMOS transistor and then PMOS transistor for implementing the good switch. Okay, so this is because of this property, right? And then in the previous class, we also learned about the power consumption. Actually, this is very important topic in the computer system hardware, because as I mentioned, so actually power is the cost. Okay, so which means that, so so actually the circuit, the most transistor circuit is connected to the VDD and ground. Okay, and then so based on the some input signal value, like the input gate level, then the output value is also changed. Okay, so which means that actually the electric charge is moved to the some capacitance of this output node. Okay, so this is the output node. So when electric charges move in a circuit, then the power is consumed. Okay, and then if the power is consumed, so if we just consume some electric power in our home, then we need to pay money, right? So actually, so that's what, so that's why the power is very critical. This is the cost, and then actually, we need to reduce the cost for running computer systems, also other digital systems, right? So we need to reduce the cost, and then we need to improve the performance. That's why we are learning about some computer hardware, and then computer architecture, and then also computer systems, right? So, and then we can classify the power consumption of a circuit as the dynamic power consumption and static power consumption. Okay, and then we can define the dynamic power consumption as the power consumption by changed input and output signal levels. Okay, so this is the equation of the dynamic power consumption. Okay, and then actually in the previous class I did not explain about the activity factor. Okay, so this is the example of activity factor. So actually we did not learn about the clock signal, but clock signal is the periodic signal. And then actually, as you can see, in a clock period, the clock signal changes its value from 1 to 0, and then 1 to 0, and then 0 to 1, right? So the activity factor of a clock is 1, and then data switching once per clock. So actually, as you can see, this is the data. And then you can find that at the clock edge, so it's a rising edge of the clock, then data value is changed for every rising edge of a clock. So for this data, that we can define the activity factor is 0.5, and then for the random data, it's a 0.25. And then actually for the typical data, so we can observe that the activity factor is nearly 0.1. But if we just consider the dynamic power consumption, actually this activity factor is determined by a software or application. Okay, so we can also we can also control the behavior of software in a computer system. So we can also reduce some dynamic power consumption. How? By decreasing activity factor. Okay, and then so if you see the this equation, they can find that this is the capacitance. Okay, capacitance, and then I mentioned that the capacitance is determined by area. The area of chip. Okay, is area. So actually, if we just use the smaller, so if we just implement the some chips using a smaller area of silicon die, then we can reduce the capacitance. Okay, so the area is also so important. And then this is the supply voltage. Then this is the clock frequency. Okay, and then also so we need to also consider the static power consumption. So actually, in the old computer systems, dynamic power consumption was critical, and then the static power consumption was not critical. But recently, the static power also occupy the large portion of the total power consumption. So and then, so actually, this is the definition of static power consumption: the power consumed when no gates are switching. Okay, so when I explained about the dynamic power consumption, actually the dynamic power is consumed when the input and output signals are changed. Okay, so when but static power is different. Even though the input and output signal values are not changed, the power is consumed. So it is because, so think about the inverter circuit. So this is the input, and then input is connected to the PMOS transistor and NMOS transistor, and then this is the ground, and this is the VDD, and then this is ground, and this is the output. Okay, so Y, output node Y. So actually, if we just analyze the behavior of this inverter circuit, so if A is high, then the PMOS transistor is off, and then this NMOS transistor is on. So actually, if we just consider this 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 node, this connection, the connection from VDD to ground, then we can find that the one of transistor is off. So inversely, so A equals 0, then PMOS transistor is on, and the NMOS transistor is off. So actually, the NMOS transistor is disconnected. So the VDD is not connected to the ground. So this is the ideal. This is ideal behavior of the PMOS and NMOS transistors. But I mentioned ideal, so which means that in reality, actually, the current can flow through the PMOS transistor or NMOS transistor, even though one of these transistors is off in the off state. Okay, so this is the real. It's a real characteristics or real behavior of most transistors. So it is because transistors. So actually, as I mentioned, our world is not ideal. Okay, and then it's the same. Actually, devices are not ideal. Okay, so which means that even though the transistor is all in the off state, then current can flow. So actually, this amount of current is smaller than some connected the current in the connected circuit, but anyway, the current flows, and then this current is called the leakage current. Okay, so which means the leakage current can flow from VDD to ground, and this leakage current is the IDD. So this, because the leakage current flows from VDD to ground, then static power is defined like this equation. Okay, so IDD multiplied by supply voltage, because you know the P equal IV. Okay, so this is the static power consumption, and then as I mentioned in the modern digital devices, static power consumption also occupies very large portion of total power consumption. Okay, so this is just the example. So estimate the power consumption of a mobile phone running Angry Birds. It was very famous mobile game, right? But I think it's not famous now. So we can define the supply voltage like this. It's a capacitance, and then it's a clock frequency of a processor, and then this is an activity factor, and then this is leakage current. Okay, so actually P, the total power, is the dynamic power plus static power, right? And then we can also apply the dynamic power equation, and then also static power equation for measuring the total power, right? So alpha C VDD square and F. This is the dynamic power consumption of a processor, and IDD and then VDD. So this is the leakage current, and then this is VDD. So just apply these numbers, and then we can calculate the total power consumption of uh, this software. And so Angry Bird running on a certain mobile processor. And then so another example. So in the ideal state, so it's no application are running. So no applications are running, but the phone has an 8 watt-hour battery, and then this is the idle state. So no applications are running, but because of the static power consumption, the power is consumed in this mobile phone. So this is the number. Then we can calculate the static power consumption of this phone, and then we can calculate the we can estimate the battery life of this phone. Okay, so this is the end of the chapter 1. Okay, and then actually in the chapter 1 we just discussed about some basic concept of the digital design, and then the required knowledge, so like some basic knowledge regarding the transistors, and then some circuit design. Okay, so this is a somewhat low level topics in this course, and then actually to understand some detailed understand that these topics, then please read the textbook. Okay, so now we are going to the digital world. Okay, so we will learn about the Boolean equation. So you can find the Boolean. Okay, it's a Boolean. Actually, the Boole is the name of a person, is the name of a scientist. Okay, actually, he defined some logic equations by using 0 and 1 only. That's why. So we are learning about some digital system, and then as I mentioned, a digital system handles digital signals, and then digital signals can have only 1 and 0. Okay, so it means that if we just learn Boolean equations, then we can understand. So we can understand some behavior, and then we can specify some behavior of a digital system. Okay, so that's why we we learn about the Boolean equation. Okay, so this is just the equation. Okay, so people are learning about the Boolean equation, then let's learn about the combinational circuit. Okay, so as you can see, this is also, you can find a word circuit. Okay, okay, so in the previous class, we learned how to build basic logic gate using CMOS circuit. Okay, so you can think that, oh, this is so actually combination of circuits and then CMOS circuits. So you can think that, oh, so we will learn about the electric circuit again. So that's true, but so now that we can understand, so we can understand the some behavior of this circuit in a digital manner, right? So and then now we will learn about the combination of circuits. So then, okay. So let's learn about some component of logic circuit. Okay. So what can you see? You can see a rectangular box and input signals and output signals. So it looks like this. So input is given, input values are given, and then because based on some function, then output signal is generated. So a logic circuit is composed of input values, but this is a digital system, so input will have only one and zero, ones and zeros, and then output values will be generated by this digital block or digital system. Okay, output. So output values will also have ones and zeros. So these are the signals, and then so we can define a certain function like so y equal fx. So this is the function of a real is a real world mathematics. Okay, so like this real world mathematics, so we can define the function of this the system or as a logic circuit. Okay, so it's actually it's the same. So this is the input and this is the output. The output is defined by input signals, okay, based on the functional specification. So we can define any function, right? So this is okay. So it's very similar to the real world mathematics function, right? So but in a hardware system, we need to also consider timing specification. So what does that mean? So what does that mean? So actually the A, so digital input or digital signal value change like this. Okay. So in the previous class, you can also find some waveform of the clock signal and then some switching signals, right? So actually the signal values can change by time. Okay, so this x-axis is the time, and then the y-axis is the value. Okay, like the 1 or 0. This is because this is a digital value. So actually, in a real system, in a real hardware, so the input value, the digital values, digital signals, the value of digital signals changes by time. Obviously, right? So in a real world, we need to consider time, right? So actually, so in the today's class, I was late. Okay. So in the real world, so we need to consider a time. So actually, the signal values change by time, right? And then if the input is given like this, then output value will be also changed. Okay? So based on the certain functions, the specific functional specification. So for example, if y equal not of a, so this is the functional specification of the not gate, right? So we already know this equation, right? So if the value of a is inversed, right? But in the real world, actually, we can observe delay. So what does that mean? So when the input value is changed, right? So input value is changed at this point, but after some delay, okay, it's a t, then the output value is changed by input value after some delay. Okay, so you need to understand some real world behavior. So as I mentioned, we need to consider time in the real world behavior, and then it's also same for the circuit. In the circuit, the input is changed, the output can be changed, but in output value is changed after some delay, some time. Okay, so this delay is also specified in the logic circuit. Okay, so it's the same. After some delay, the value is output value is changes. So it is because. So actually, when I explain about some inverter circuit, actually, so like this is. So if the y is changed from 0 to 1, then we need to move electric charge to this capacitor, right? And then, but it takes time, right? So think like this. So this is, we have a certain water bottle, and then we want to fill this water bottle. So you can understand this is the water bottle, the capacitor. So in a capacitor that we can fill electric charges, right? So like the water bottle. So in my water bottle, that we can fill water, but it takes time, right? So what I want to say is that it takes time for it takes time filling electric charge to capacitor. Okay, because of this time, then we can observe delay in a circuit, and then which means that the timing specification, this delay. So we need to also specify timing characteristics, timing property of a logic circuit. But because this is a real circuit, right? So actually, it's just I believe you can easily understand the input values, output values, and then functional specification. But this the system, this the hardware. We also need to consider timing specification. Okay, like the delay from input to output. Okay, okay. Oh, so this is the definition of a circuit. So actually, I copied this definition from Wikipedia, right? So Wikipedia is a very good site, right? Okay, and then now, so actually, so recently we can ask question to ChatGPT or the Copilot of Microsoft, but we can also Google. We can also search some terminology in from Wikipedia. Okay. So what is the definition of a circuit? Electric circuit is composed of individual electronic components. So these are examples of electric components: resistors, transistors, capacitors, blah blah blah. And then these components are connected by wires, so conductive wires. So it's conductive wires means that it means that it's a conductor, right? The electrons. So electric charges can flow via conductive wires. So this is a definition of electric circuit, an electric circuit. Okay. So electric circuit includes some components, electronic components, such as these components, and these components are connected via conductive wires. And then through these conductive wires, electric charges can move. So this is a definition, okay? A definition of electric circuit, okay? Okay, then, so in a digital system, so actually we can build a digital system using the electric circuits and then using transistors and then some components. Actually, we can find some components such as the resistance, inductance, and capacitance in the transistor circuits. Okay, so by combining, by building electric circuits, then we can build logic circuits. So this is an example. So you can find a large rectangular box here, and then inside of a box you can find the smaller, like the E1, E2, and E3, the smaller boxes in this large box. So if you see the definition of the logic circuit, so actually these are components of the logic circuit: input, output, functional specification, and timing. Okay, so if we just apply this knowledge to this large box, so this is the large box, okay? So you can find some input signals here and then output signals of this large box, okay? So this is a certain circuit, right? And then, but we can also combine smaller circuit elements, okay, smaller circuits to build larger circuits. So by combining these smaller circuits, then we can also build a larger circuit, okay, a larger circuit. So this circuit is also called a module, okay. So this is a smaller circuit, okay. So this is the hierarchical design, right? So in the first class we learned about the digital design concept. So this is the kind of a hierarchical design. So by combining smaller elements that we can make the larger circuits, okay, larger module. Okay, but if you see the inside of this large module, then you can find that. So you can also find the input and output of this smaller module, right? And here, here, and here, here, and here, and here. And then output and input of this module are connected, right? So in this example, so as you can see, the output of module E1 is connected to the input of module E3. So it's an electric component. Okay. So In this figure, we call this connection, the connection from the input output to the input, we call this connection is the node. And then this node is in the inside of is the inside of is inside of the large module. So that's why this module is called this node. This node is inside of the large module. So this node is called the internal node. Okay. So this is definition of a circuit. So we can also combine smaller modules or smaller circuits to build larger circuits. Okay, and then in order to build a larger circuit, then we can just connect the output port and then input port of two modules, so different modules. Okay. Okay. Now, so let's learn about the types of logic circuits. Okay, so there are two types of logic circuits. This is very important. Okay, so combinational logic and combinational logic and sequential logic. Okay, so as you can see, you can find that combinational logic is the memoryless. So what does that mean? So what is memory? So memoryless. So memory means that. So what is the memory? Definition of memory in a real world. So we can we can easily say that I memorize something. What does that mean? It means I memorize. So it's I store. So I just store previous events in my brain. To understand? So I mentioned memory. So memory means that we can just store previous events, okay, or state. Actually, this is a definition of memory, right? Then what does that mean? It's memoryless. The previous event or previous states are not stored, okay? It means output. Output is just a function of input, okay? Current values are just a function of current values of input. So combinational logic is memoryless component. Okay, so it means that the output like this one, the output of combinational logic is determined by only current values of input. So this is a definition of combinational logic. Then what is a sequential logic? Sequential logic has memory. So what does that mean? The output of this sequential logic is determined by input and previous state. This is definition of sequential logic. So firstly, we will learn about the combinational logic in this course, and then we will learn about the sequential logic. Okay, so because as you can see, the combinational logic is easier to understand because the output is determined by only current input, right? So sequential logic, but sequential logic is determined by previous state. Okay. Okay. Then So, okay, then how about the inverter? So this is the A, and this is the symbol of inverter, and this is the Y. So when we define behavior of an inverter, then, you know, the Y, the output Y is just defined by current input, right? So which means that inverter is a combinational logic. Do you understand? Okay. I hope you can understand. So these are rules of combinational logic, combinational composition. Okay. So this example, so you can find the AND gate here. This is the AND gate. This is the AND gate. This is the OR gate, right? So then AND gate is a combinational logic. Is AND gate combinational logic? Right. It is because, you know, the Y output of AND gate is determined by only inputs like A and B only. So AND gate is a combinational logic. How about the OR gate? OR gate is a combinational logic also, right? And then also we learned by combining a smaller circuit that we can make larger circuit like this, because by connecting output port and input ports, then we can build a larger circuit, right? So this is also actually combinational logic. Okay, we combined two AND gate and one OR gate, then we can make combination logic. Why? So, you know, this is the output and these are input of this logic, but output is just determined by combination logic. Okay, so this is the rule. Every element is combinational. Okay, so in this example, this large circuit includes two AND gate and one OR gate. And then, you know, as I mentioned, AND gate is a combinational logic and OR gate is a combinational logic. So all elements are combinational, okay? And every node, this is the node, okay? This is node, this is node. Every node is either an input or connected to exactly one output, okay? So, you know, okay? So this is buffer, this is buffer, A, B, this is inverter, actually. So you can find, oh, this is node, but actually it's not, this is incorrect circuit. So it means that actually two outputs are connected to one input. Actually, this circuit does not work correctly. Okay, so this input is connected to exactly one output. Okay, okay, and then the circuit contains no cyclic path. So what is a cyclic path? So output is connected to a certain input of element. So this is feedback path, the cyclic path. But in a combinational logic, the circuit does not include any cyclic path. So these are rules of combinational composition. Okay. Okay, then these are examples. So some problem. But so just I am speaking just I speaking. Okay, so which are combinational circuit? So based on the previous combinational composition rules. How about this? So this is inverter, and this is inverter. Oh, two inverters. So those are combination logic. And then it's connected and connected and connected. Two inverters are connected and no cyclic path. So this is the combinational logic. So it's a CL. So I frequently use this kind of symbol to represent this logic is combination logic. So this is combination logic. How about the B? This is not a combinational logic. Why? Because there is a cyclic path. Cyclic path. So output is connected to the input. Oh, this is not a combinational logic. How about this? It's the same. CL. Combination logic. So you know this example. Okay. How about this one? As I mentioned, this is not a combinational logic. Actually, this is the incorrect circuit. So which means, so you know, output, two outputs are connected to one input. Okay, and then actually this circuit will not work correctly. Okay, if so, output is the driver. Okay, if two drivers are driving one input, one node, then this will not work correctly. Okay, so this is not a combinational logic or combinational circuit. How about this one? This is a CL and this is CL. It's a combinational logic. Oh, so okay, it's okay. So this is the also combinational logic. How about this? Oh, we can find the cyclic path here. This is not a combinational logic. Okay, so this is very important. So we need to classify. We need to distinguish combinational logic and sequential logic in this course. Then you can just understand a combination logic is the memoryless, sequential logic has memory. Okay, so this is the function of combinational logic. This is a function of sequential logic. Okay, and then by combining multiple combinational logic, then we can make also larger combinational logic. Okay, this. So these are some rules of combinational composition. Okay, and then this is the, so based on the rules, then we can figure out the which we can figure out combinational logic, right? Okay. Okay. Now let's learn about the Boolean equation. So this is a definition of a Boolean equation. Okay, so as I mentioned, Boole is a name of a scientist. Okay, so Boolean equations deal with variables that are either true or false. Okay, so this is a definition of a Boolean equation, right? It just handle variables, and then these variables have only true or false value. Okay, so in a digital manner, so we can think that true is 1 or high voltage is a VDD, and then false is 0 and it's the ground, right? So if we just represent the behavior, the functional specification or functional behavior of our digital circuit, then we can represent the behavior. We can represent the functional specification of a digital circuit using Boolean equation. Okay, the functional specification of outputs in terms of inputs. Okay, functional specification like f of a circuit. So this is an example. So this is the combinational logic, right? And then this combinational logic has three input signals A, B, C in, and then two output signals. Okay. Then we can define the function of this one of our output signal using input signals like this. So S is the function of A, B, and C in. So this is the combinational logic, right? So only the current signals, current values are used as the inputs of this functional specification. How about the C out? C out is also the function of input signals. And we can define the functional specification of this circuit like this. S equal A, this is exclusive OR, and this is also exclusive OR. A exclusive OR, B exclusive OR, C. C out, A, B. So this is product. What is this one? This is AND, right? How about you can find the sum. What is this one? This is OR, right? So A and B or A and C or B and C, right? This is the Boolean equation of C out. So actually this is the full adder. So we'll learn about the full adder later. Okay, so we can define Boolean, we can define a functional specification of combinational logic or any logic circuits using Boolean equations, right? Okay. So these are definitions. So definitions you need to memorize. Okay. So definitions. Okay. Okay. So let us assume that this is the circuit, right? And then we can define some input signals and output signals is defined by input values, right? As a functional. Okay, this is the kind of combination logic. Okay, okay. Complement. The first definition is complement. The complement is the variable with a bar. So what is this bar? Bar represent inversion. Okay, so it's not. So a bar is the not of A, B bar is a not of B. Okay, so complement means that it's a variable with a bar. Okay, and then literal. Literal represent variable or its complement. So we can use the A or A bar. Okay, so we can think that these are literal. Okay, and then implicant. Implicant is the product of literals. Okay, so what does that mean? So what is the product? Like A, B. So this is a product of A and B, right? So actually this is the A and P, right? But I mentioned that when we learned about the basic logic gate, we learned that So we can represent AND gate like multiplication, like product, right? So implicant represent a product of literals. Okay, like this. This is the example of implicant. And the mean term is a product that includes all input variables. So this is a definition of mean term. So this is an example. So I we assume oh, this is a logic, and then this logic includes 3 input signals, right? And then if you see this implicant, okay, this implicant includes all input variables A, B, and C, right? So we can call this is a mean term, okay? A product that includes all input variables. And the max term is the sum that includes all input variables. Oh, this is the example of max term, okay? So then you can find sum. What is sum in a Boolean equation? Sum A plus B. So it is A or B, okay? So we can represent the OR gate using sum. Okay. So max term is the sum that includes all input variables. Like so, you know, A, B bar, and C. So it includes all input variables A, B, and C. And then you know this is the sum. So this is a max term. So you know these are it's a definition, right? So you need to memorize the definitions, right? So you can and then these are definitions of a certain terminology. Okay, and then also when we learn about the equation, then we also learn about the priority of operation. So like the order of operations. Okay, so it's related to the priority. So for example, in the real mathematics, like is in the real mathematics, so y equal ab plus c. So we already know that the multiplication has a higher priority than addition, right? Because so for this equation, we firstly perform a multiplied by b and plus c. So we in our equation, we need to define the priority of operation. So it's true for the Boolean equation. Okay. So and then this is the order of operations. Not has the highest priority. Okay. So and then it's followed by and, because and is similar to the multiplication is the product. Okay. Small. So and then you know the multiplication has a higher priority than addition, right? And then or it's a sum. So this is the example. Y equal a plus b multiplied by c bar. The firstly, this is performed. So we need to calculate the c bar. Okay, so it's a not of a c and then bc. It's a multiplication. So then we need to perform b and c bar. And then this is or. Okay. So this is the order of operation. Okay. So we can say the firstly not has the highest priority, and then and then or. Okay. So I believe you can easily understand because we are very familiar with the order of the priority of multiplication and sum addition, right? Okay. Okay, so another terminology is the okay. We can represent a Boolean equation using two different types of it's a form. Okay. Okay. The first type is a sum of products called the SOP form. So all Boolean equations can be written in sum of product form. Okay. So we can represent a Boolean equation using sum of products. So what is a sum of products form? What is a product? Product is the AB or BC or CA like this. So these are products of literals, right? And then these products are summed. uh, Summed, okay, is a word. Okay. So this is the sum of product form. Okay. Okay. So this is the some example. So example of the truth table, right? So this is the truth table. And then in the truth table, so we can define all possible input values. So in this example, this table has two inputs. Okay. So we can define four different cases: 0, 0, 0, 1, 1, 0, 1, 1. Okay. And then for every input values, where we can define output like this. Okay. So if we just observe this truth table, you can define mean term. Okay. Mean term is the product of all variables, all input variables. Okay. And then this mean term represent inputs that can make output 1. Okay. So this example, so in order to make this output 1, then the A multiplied by B, so this is the A bar and B bar, A bar multiplied by B bar, so this is the A bar and B bar. So for only this case, if A is 0 and B is 0, then Y will become 1. Okay, so this is the mean term of this law. Okay, so in order to make Y equal 1, then this mean term should be A bar and B bar. Okay, then if A is 0 and then B is 0 and then A bar, B bar becomes 1, right? Okay. So this is the mean term of this law, and then you can find the mean terms of other laws like this one. So actually, if you can easily understand that, if input is 0, then is bar. We can use the bar. Okay, bar here. And if input is 0, and you can use the bar here. And the input is 1, then we can just use the each variable. Okay. So I mentioned that in order to make y equal 0, 1, then we need to use this mean term, right? But in this example, output y is 1 only for these rows, okay? Like 1 and a bar, and this row, so a is 0 and b equal 1, and then y becomes 1, and then a equal 1, and then b is 1, then I becomes 1. So only for this row, the y becomes 1. then how can we represent this function, this logic using a Boolean equation, using uh, using a min terms, okay? It's a SOP, so sum of a product form. So we can just combine, like, so using this min term and this min term, okay, A bar multiply B plus A B equal Y. This is the SOP form of this logic. Okay, so by analyzing a truth table and then by combining min terms that will make the output 1, then we can make a Boolean equation of this function, this logic. Okay, understand? So actually we can just combine this low and this low. So this is 1, and then we can just use also the min term number here, the 1 and 3. But actually we just combine the Boolean equation like this. Then another term is the product of sum. So so until here we learned about the SOP, the sum of a product. We firstly define min terms, the product, then we just add the sum, these min terms is a sum of a product. The another type is the product of sums, POS form. So for the sum of a product form, then we can just define max term, okay, like here. And then each max term is false for then low, okay. So what does that mean? Actually, for this sum of product form, we can directly uh, understand based on the truth table, right? But the POS, the product of a sum, is a little bit different. So firstly, we need to define max term because this is the sum. Firstly, we can define sum. So this is the max term. Then these sums are multiplied each other. Okay, so this is the sum of a product of a sum, product of sums. Okay, but in order to make the equation, this is a little bit different for actually, right? So because so actually we need to define the max term that can make output 0. So what does that mean? So the POS sums, so we can actually in the SOP form, so we just select the low that can make the output value 1 for this min term, right? But for the product of sum, then we need to first define the max term that can make the output 0. So for this A, B, so it means that if A equals 0 and B equals 0, then the Y becomes 0, right? How about the other values like A equal 1 or B equal 0? Then Y will be 1, right? For this equation, the max term, A plus B. So we can select the max term that can make Y 0 for this input, okay? So if the A is 0 and B is 0, then this is the A and B, not A bar. So when we select the max term, then actually this the A is the A. So A is its own variable for the if A is 0. Okay. So this is max term, and this is the another max term, and then we select max terms that can make Y 0. the output 0. So this max term and this max term, okay, like the A plus B. So this is the max term, and then A bar, because A is 1, A bar plus B. And then this is multiplied. Okay, then and because we just select the max term that can make y 0, then it will make y 0. Because and then so if one of these max term is 0, right? So if 0 and or the 0, then this y will become 0 because this is the end. So the max term, when we just when you just make a Boolean equation of a certain function using a product of sums, then firstly we need to select a max term that can make y 0, output 0. Then these max terms are just multiplied. So we can make the product, then the output will be 0. Okay. If one of the max term is 0, then output will be 0. So that's why the max term is, so we need to think inversely for the product of a sum. Okay. So we need to select the max term that can make y 0. Okay. Then these max terms are multiplied like this. So this is the, so this is the product. The capital pi represents the product, and then this is sigma. It's a capital sigma. So sigma represents the sum. So it's a product of sum form. Okay. Okay. So also all Boolean equations can be written in POS, product of sum form, but you can intuitively, I believe you can intuitively understand this sum of a product form. Okay. But when we make POS form, then you need to understand that. So firstly, we need to select a max term that can make y 0, output 0, and then these max terms are selected for making the sum. Okay. Okay. So I will stop here, and then so actually, so in this time, we learned about some definition of, actually this class is, so today's lecture is very important. And then sorry for the some canceled lecture, but today's lecture is very important. So firstly, you need to know definition of combinational logic and sequential logic. Okay, and we learned about the Boolean equation. So we will use Boolean equations to represent functional specification of a logic circuit, right? And then also you need to memorize the definitions like complement, retro, implicant, min term, and max term. And then all Boolean equations can be written in SOP or POS forms, right? And then you need to know how to make Boolean equations from truth table used for the POS form and SOP form or POS form. Okay. Okay, so I will stop here, and then I hope you can watch this video before the next class. Then sorry again. Then thank you for listening, and see you in the next class. 감사합니다.